Hello everyone, in this video we are going to solve another problem related to bending, which is the second exercise problem from the chapter of bending in the book of Mechanics of Materials by R.C. Hibbeler. In this problem we are being asked to determine the reactions at point A, which is the point where the wing of the aircraft is fixed, and then we are also being asked to draw the shear and moment diagram for the wing. The loading condition is given like dead weight loading that's acting on the wing, the point load that is caused by the fan, and the reaction of 75 kilonewton is also being given to us. So this is the loading condition at the wing. So let's solve this problem. This is first part of the solution of this problem. Since this is a very long problem, in this part of the video we are going to solve for the reactions that are acting at point A. In the respective parts of solution for this problem, we will draw the shear force and bending moment diagram. So let's first draw the free body diagram of the wing. So let's consider the wing on which these loadings are being acted. There are some point loads there, 15 kilonewton at a distance of 2.4 meter from the left hand side. The reaction at 0.9 meter from point A. Here are the distances between the exterior ends and the distances between the two forces acting on it. And there is a trapezoidal loading from point A up to the 15 kilonewton force, and afterwards there is a triangular force. So this is the free body diagram of the wing. The first thing that we are going to do is the reaction at point A. Since this wing is fixed to the aircraft at point A, so there will be three different type of reactions: horizontal force, vertical force, and moment. Before we calculate those reactions, we need to convert these trapezoidal loading into the point loads, and also the triangular load should be converted into the point load. So let's first convert this trapezoidal load into the point loads. So to deal with this trapezoidal, we need to convert this trapezoidal into two parts like this way, so that we can have a uniformly distributed load that will be over here, and as a triangular load over here. So the uniformly distributed load will have magnitude up to this point, and the triangular load will have magnitude, the rest of the magnitude. Since the total is 6 kilonewton per meter, and up till here, if you look at here, you can see up till this point is 3.75. So this is 3.75 kilonewton per meter. The rest is actually 2.25 kilonewton per meter, because the total is 6 kilonewton per meter, and up to this point we know from here it's actually 3.75. so 3.75 plus 2.25 will make it 6. Now we have UDL of 3.75 kilonewton per meter up to a distance of 0.9 plus 0.6. So it means after a distance of 1.5 meter, we have UDL of 3.75 kilonewton per meter. So the point load would be calculated as 3.75 multiplied by the distance, which is 1.5 meter. So on multiplying these, we will have 5.625 kilonewton as the point load acting on the behalf of this UDL. And for the triangular load, we know that the formula is actually the same like the calculation of the area. Like we have this 3.75 as the height, and the base is the horizontal distance. And in that case, it was simply like a rectangle. So in that case, the formula was like that. But this is a triangle, so we know that the calculation of the area is also like half multiplied by the altitude, which is in this case is 2.25, and the base, which is 1.5. So this will be 1.6875 kilonewton. So now instead of this trapezoidal, we have 2 point loads, one of magnitude of 5.625 kilonewton. So as we know that the UDL would be acting at the exactly mid of the distance, the distance is 1.5 meter, so then this distance will be 0.75 meter. And in case of triangular load, the point load would be acting at 1 by 3 from the larger side and 2 by 3 from the smaller side. So the larger side is actually from point A. So this will be then distance. Magnitude is 1.6875 kilonewton. How about this distance? This distance will be like total distance is 1.5 meter. So by 3, which will be 0.5 meter. So this is 0.5 meter distance. Now in a similar way, this triangular force should be converted into the point load. So the formula would be half. The base is 2.4 meter. The magnitude at the larger side is 3.75. So this will then be equal to 4.5 kilonewton. Now instead of this triangular force, we have a point load that has magnitude of 4.5 kilonewton. How about the distance? The distance from the shorter side would be 2 by 3 and distance from the longer side would be 1 by 3. So I take from the shorter side this time. So the total is 2.4 meter. So it will be like 2 by 3 of 2.4. That will be 1.6 meter. Now this is what we have. So after having all the forces on this wing, the next thing that we are going to do is the calculation of the reactions at point A. Since this wing is fixed to the aircraft, therefore there will be 3 reactions as I told you before. So there will be a 1 horizontal force, 1 vertical force, and there will be a 1 moment. So let's represent the horizontal force with FH, vertical force with FV, and moment as MA. So these 3 we have to determine. Now if you look at the loading condition of the wing, we can see that there is no horizontal force acting on this wing. Therefore this horizontal force would be equal to 0, but since different vertical forces are acting on it, so therefore we need to determine this FV. So I consider the direction of FV as upward, and let's apply the conditions of equilibrium. The second condition of equilibrium, which is summation of all forces acting in vertical direction equal to 0, and I consider all the upward forces as positive. So all these forces which are acting downward will be negative. So negative 4.5, negative 15, negative 5.625, negative 1.6875, and the 75 kilonewton is acting upward, hence positive. And I consider the FV, the reaction at point A, as upward, hence positive. So in this equation we can see there is only one unknown, so then FV can directly be calculated. So on doing calculations, we are going to get the value of FV as negative 48.2 kilonewton. Now this negative sign indicates that what direction we have considered for FV, which was upward, but will not be upward, it will be downward. So you can then modify the things accordingly. You can change the direction over here and the sign positive to negative, so this will then be positive. So this is one of the reaction that we have got. The other reaction that we are in need is the moment acting at point A. For that we need to apply the third condition of equilibrium, which is summation of all moments acting at any point equal to 0, and I usually take clockwise moment as positive. It's up to you whether you take anti-clockwise as positive. So I take the point as A. So I take summation of all moments acting at point A equal to 0. So I consider the moment acting at point A is anti-clockwise, that will be means negative. The moment that will be caused by this 1.6875 will also be anti-clockwise, hence negative 1.6875. The momentum will be 0.5. This 5.625 will also be causing anti-clockwise moment, hence negative 5.625 multiplied by the momentum, which is 0.75. Now the 75 kilonewton will have clockwise movement and the distance is 0.9 from point A. The 15 kilonewton will have anti-clockwise movement, hence negative. The distance will be 1.5 meter. 4.5 kilonewton force will also be creating anti-clockwise moment. The momentum will be 0.9, 0.6 plus 0.8. This distance is, the total is 2.4 meters, so this will be then 0.8. So 1.5 plus 0.8 means 2.3 equal to 0. So on doing calculations, we are going to get the value of MA as 29.6 kilonewton meter. Since the value came out to be positive, it means whatever direction we have considered is correct. If it would have been negative, then in that case we need to change this direction. Luckily we have got positive. It means the considered direction of the moment is correct. So we just have got the reaction at point A.